Hey, good morning, Chem 20s. Today I want to talk to you guys about polarity. You have known for a while, you knew since Science 10, we talked about water being a polar molecule. Well, really, what does that mean? What does it mean to be polar? Why are some molecules non-polar? Well, it has to do about the electrons that are in the atoms of the molecule. Is the charge distributed symmetrically, evenly around the molecule, or unevenly? And so nonpolar molecules are symmetrical electron distribution. And with a polar molecule, it's not symmetrical. There's more electrons on one side of the molecule than there are on the other. And so just a general guideline of the different molecules that are polar and nonpolar. Is it diatomic? Is it trigonal planar? Or is it tetrahedral? So we're going to talk about how do we decide if a molecule is polar or non-polar. And so there's two kind of major things that you have to do to figure out if a molecule is polar or not. The first thing you need to do is look at the electronegativity difference between the atoms in the molecule. And we call this the bond polarity. You're asking yourself, is the bond polar or not polar? And so you look at the electronegativity difference between the atoms that are found in the molecule. So if the atoms have the same electronegativity, or if it's a close, the value of the electronegativity difference, the change in electronegativity or the difference is between 0 and about 0.5, then you can say that they're sharing those electrons equally. And we would say then that that is a non-polar covalent bond. What about if there's an unequal sharing? Well, in that case, there's a difference in electronegativity. So when we look at our electronegativity values on our data booklet, and oh yeah, just a reminder, where do we find those electronegativity values? Well, here's our data booklet, right? You have to find the electronegativity difference between the different atoms by looking at these values here. There is the value that shows the electronegativity, okay, just below the atomic number. So you look them up in your data booklet. Okay, so back to our notes. How do we determine? Well, if the electronegativity difference is between about 0.5, and again, this is just kind of a rule of thumb, a general value between 0.5 and 1.7, that's a fair difference. And those atoms are not sharing their electrons equally. The higher the electronegativity difference means that one atom has got a lot more ability to attract electrons, and therefore they're not sharing equally. And we call this a polar covalent bond. And in fact, if we have a really large electronegativity difference, and what do I mean by really large? Well, we're looking at electronegativity differences or changes of electronegativity values between the two atoms between 1.7 and 3.3. We would say that that's such a big electronegativity difference that we would actually call that an ionic bond. Now, there's some right, so we would say that big of an electronegativity difference. Typically, we're going to have a metal and a non-metal in that compound. But like I was just starting to say, you're going to find even some covalent molecular compounds that have a really big electronegativity difference. And so they act like, or they behave like ionic compounds because there's such a big difference and such an inequality in electronegativity values between the two different atoms. So as I mentioned, you have to find your electronegativity differences between the atoms and look up those values in the data booklet. The second thing we'll talk about later in this booklet to determine if a molecule is polar or not is you look at the shape. The molecules, you draw out the Vesper diagram and you ask yourself, is the molecule symmetrical or not? What is the symmetry? Is it equal in terms of the atoms, how they're distributed all the way around or not? Okay, so next page, as I mentioned, you have to look up your electronegativity values and you are going to determine, are they similar or are they different? And then use the little continuum, the little chart on the bottom of this page to determine is that bond polar or not polar. So here's an example, HCl. And I've gone and I've looked up the electronegativity values in my data booklet. So hydrogen is 2.2 and chlorine is 3.2. So the electronegativity difference between these two atoms is 1.0. So I go 3.2 minus 2.2 and I see that the difference is 1.0. So what does that mean? Well, that means that when you look at your little continuum on the bottom, that is in between a value of 0.5 to 1.7. So we would say that the hydrogen and the chlorine are not sharing the electrons equally. What happens is we have a partially positive end of the molecule where there's less electrons. And we indicate that by this funny little symbol, and it's a Greek letter delta. It's the small letter delta with a positive, saying this is the more positive end of the molecule, where less electrons are, because hydrogen is not as strong as attracting electrons as chlorine is. So on the other hand, here's this little delta negative, and that's around the chlorine atom, and that means that this is the partial negative end of the molecule. These two atoms are not sharing the electrons equally. The electrons are more around the chlorine, right? Remember, he has 3 lone pairs of electrons. So the electrons are not shared equally. And so just looking at the electronegativity difference, looking at our little continuum, we would say that this is a polar covalent bond, right? We have 2 nonmetals, they're sharing electrons, but they're not sharing equally, okay? Chlorine's an electron hog. All the electrons are more around the chlorine end of the atom and not so much around the hydrogen end of the atom. So how is that different from a nonpolar covalent bond? Well, typically you look at a nonpolar covalent bond and they're going to have equal electron sharing. So you go and you look up chlorine, what we just did. So you know that chlorine's electronegativity is 3.2. And here's another. This is a diatomic chlorine molecule. Well, what's the electronegativity difference? Nothing. The electronegativity difference is 0. There's no difference between them. And so there's no dipole, there's no bond electronegativity difference. What's that mean? This means that there's equal sharing of electrons. These guys are going to form a covalent bond that is nonpolar. Okay, a nonpolar covalent bond. We just said that the electrons are going to be more around the chlorine end of this molecule because of the electronegativity difference, right? 2.2 versus 3.2. So we can actually show using a little arrow like this, that means that the chlorine is the more electronegative end. The electrons are going to be hanging out more around him. We would say that that's a dipole that is forming there that's more electronegative than the hydrogen. Okay, and so again, use your little continuum here, your little general rule down at the bottom to decide what's the electronegativity difference. Is it covalent, nonpolar, is it polar, or does it behave like an ionic compound? So a couple of practice problems we can look at. And again, you are looking at the electronegativity differences here just to determine is that bond going to be polar or not. So I'm actually going to move this down. We did A already, so I'm not going to redo that for you, but we can certainly take a look here at letter B. So we've got carbon and we've got hydrogen. These two guys are making a bond. Carbon we know is a nonmetal and hydrogen is a nonmetal as well. So now you go and you look up in your data booklet and find the electronegativity of carbon. And you see, well, that's 2.6. Write it down. Hydrogen, 2.2. So which guy is the most electronegative? Well, it's going to be carbon. And so the electrons are going to go more towards the side of the carbon. But when you look at your bonding continuum and the general rule, you see that this electronegativity difference, the change in the electronegativity, is 0.4. And so that means that this acts as a non-polar covalent bond. So even though there is this electronegativity difference, I'm not going to show my bond dipole because we are close enough to say that these guys are pretty close to sharing fairly equally. Now I'm going to compare that to E here, MgS. Well, that's interesting. Mg, that is a metal. And I have sulfur. Well, we know that that guy is a nonmetal. So what's going to happen here? Well, by definition, this is an ionic compound. Not to say that, right? Not to say that molecular compound can't behave like an ionic compound. It sure could if there's a really high electronegativity difference. But when you look at the electronegativity values of these two guys, here's our metal. Magnesium is 1.3 and the sulfur atom is 2.6. So what's the electronegativity difference or the change in electronegativity? Well, it is 1.3. So 2.6 minus 1.3 is 1.3. And that certainly falls within our polar covalent value. Even though it's an ionic compound, the electronegativity difference falls within the range of 0.5 to 1.7. So even though it is an ionic compound, it behaves like a polar covalent compound. And so we have this dipole created where there's more electronegativity, that is going to be more electrons surrounding the sulfur end of the atom. That's where the electrons are hanging around. So this is a polar bond that we have here. Now we can say that, yeah, it's an ionic compound because metal, non-metal, but it actually behaves more like a polar covalent compound. All right, so I'm going to take a break there, and you guys are going to have to work your way through these questions, and then I'm going to talk about how do we determine, this is how we find out to determine if the bond is polar or not. And I'm going to come back, my next video is going to talk about how to decide the symmetry, the shape of a structure and the entire molecule, whether it is going to be polar or not. All right, signing out for now. We'll be back at you in a few minutes.